All right, so now we're going to wrap up our understanding of visual cognition and visual perception. Specifically, we're going to talk about object recognition, and then we're going to talk actually um, a little bit about something a little bit different and off the path that we've been going on about attention. What the relationship is between recognition and attention. Hopefully, you'll see by the end of this set of lectures. So just to kind of pick up where we were from last week, we've been talking about early visual cortex. We talked about the retina, LGN. We got to V1, about how it likes lines and oriented lines. We talked about V4 and its role specifically in color. And now we're going to move beyond it into other regions, LOC and VTC, and we'll get into their meanings later. And the main idea that we're going to talk about with these, just to get us all together on the same page, is this conception that there's a visual hierarchy that basically, as you go further and further along the hierarchy, you go further and further down the chain of complexity, with a region like LGN liking small dots, V1 liking things like orientation, LOC, which is something we'll talk about at length today, liking basic shapes, VTC, getting to more complex shapes, and so on and so forth. So that's kind of the trajectory that we're going to go on for today. But before we dive into LO, I just want to say a few final words about V1 and V4. Specifically talking about what can happen to people who damage large swaths of visual cortex, specifically an occipital cortex of V1 through V4. So for a lot of people who damage this region, they are afflicted with a disorder that is called aperceptive agnosia. Now, aperceptive agnosia is kind of interesting because for a person who has this disorder, they have completely intact brightness, color, and motion perception. If, you have your hands go up or down or left and right, they have no problem telling you if the motion's up and down or left or right. If you show them two objects, one of which has color, the other which is grayscale, they can point to the one that's in color, no problem. So they have these real basic perceptual abilities. However, they have disordered perception when it comes to actually recognizing things like the shape, a picture, letters, numbers, and so on and so forth. The idea is that they can process the basic ingredients of the visual world, they just can't put them together into coherent wholes. So for example, if you show them line drawings of letters and numbers and you ask them to draw them themselves, you'll see that they'll do something kind of like this. And you can sometimes kind of squint and make out like maybe this is intended to be the beginnings of an A. Maybe they're only drawing two lines here with the X, and maybe they're getting a little bit of something. If you do it with more geometric shape type things, it seems like there's some circular thing they're getting here. I guess you could squint again and also see that the jagged lines are going on with the key, but they really can't even put the most basic elementary visual things together, let alone recognize what something is. However, again, they can tell you, for example, if you wanted to say like, which has more black, this shape here or this shape there, they can tell you that it's that shape there. If this square started moving left or right and up and down, they can tell you which way it's moving just fine. They just can't bring it together. Okay, so that's what happens if you damage V1 through V4, but what happens if you damage this outside part of your head, kind of into the two sides of your head right here, which is the lateral part of the occipital cortex, the sort of occipitotemporal junction. In that case, you're afflicted with another type of agnosia, but this isn't aperceptive agnosia. This is referred to as associative agnosia. Because what differentiates an associative and an aperceptive agnosic is that if you show, for example, a person with associative agnosia a picture of a key, they can draw a key just fine. They have no problem with it. Probably the limits of their drawing abilities are more about their, drawing abilities rather than their perceptual abilities. But if you ask them like, hey, what did you just draw? They're going to say things like, I don't know. They're not going to be able to tell you what it is. If you ask them to draw a pig, they can do that just fine. And they can maybe get in the ballpark, tell you it's a dog or maybe an animal, but they can't say like, oh, that was a little pig. They draw a railroad car. They might even get from the wheels that it must be something like a locomotive because they can say it's a wagon or a car. But then actually sometimes you'll still get mistakes because again, even though they can draw a bird decently well, they might say it's a branch stump or something like that. They don't even get that it's an animal. And to try to give you a conception of what associative agnosia is like, here is a picture where at first you might glance at it and think it looks like kind of a cluttered room, but then the more you look at it, the more you realize it doesn't make a whole lot of sense. And so a thing that I could have you all do in theory is you could take some time and you could draw out what you see here. But then if I asked you to describe what you saw, you'd probably struggle to do it. So like this, gosh, what is this thing? It's like a teddy bear or maybe a fur coat or something. So you could draw it quite well, but then if you were asked to identify it, you would really struggle. That's kind of what it's like with associative agnosia. You can see things just fine, you can process it just fine, but when it comes time to identify it, you struggle. So let's actually watch a video of a patient who's afflicted with associative agnosia in action. Real quick, let me just make sure the sound is on. Yeah, all right, here we go. Nope, sorry.
Here we see there are many objects around the sink. Greg has to be able to recognise each one and how it is used. For a person with agnosia, this task can be very difficult. Notice how Greg not only looks at the toothpaste, he also feels the tube in his hand. He then makes a mistake by reaching for the comb rather than the toothbrush. He knows the object is not right for the task. It takes a few seconds for him to work this out. He then chooses the toothbrush correctly. Next, Greg is looking for his deodorant. He has to look, smell and feel each item before he can correctly select the one he needs. This task could have been made easier for him by only placing the items he needs beside the sink. Too many items can be confusing or distracting.
Okay, so one thing I want to point out is that thing that she said about touching and smelling. So even though he might struggle to recognize something from looking at it, when he touches it, when he smells it, when he uses these other sensory modalities that have not been damaged, he can recognize these things just fine. You could almost imagine, like, if someone's like, grab the Sharpie, grab the pencil, what could you use if you're an associative agnosic? You would struggle maybe from looking at it, but maybe if you touched it, you'd be like, well, this is smooth and this is kind of jagged, so this must be the pencil and this must be the Sharpie. You could smell it. Sharpie has a distinct smell. So they can use other senses to kind of clue them into it. So people then started to naturally wonder, well, what then is happening in this part of the brain for people who are healthy and they don't have associative agnosia? And that's what was going to move us to this next stage in the hierarchy, where we're going to talk about this region LOC, which stands for lateral occipital cortex, which is thought to process basic shapes and contours in objects. So if LGN likes dots and V1 likes lines, LOC is kind of one of the first parts of the visual system that now combines those lines to make shapes. So how could you find and localize a region that likes these basic shapes? What would the contrast be? Because to remind you, from several weeks ago when we were talking about finding face regions, the contrast would be something like faces minus objects. But here we're not looking for that. We're looking for something else. So what would you contrast? To find a region of the brain that likes these basic shapes, what you would just do is you would take pictures of actual images and compare them to scrambled versions of those same images. So you could have 32 scrambled objects and 32 actual objects. And if you say basically, all right, show me the parts of the brain that respond more to these images than these images, you find something that looks like this. So here we're looking at what's called a flat map of a person's brain. So this is the back of the head. We've just kind of flattened it like a pizza. And you can see that these yellow parts that are getting active here, down here, this is LOC. It's beyond V1, 2, 3, and 4. And this is the first part of the visual hierarchy that really seems to respond more to these objects that have coherent contours and shapes with them. And they don't have these just these jagged lines and so forth. Just to give you some more sense of what this region likes, it's going to respond more to items like this and less so to items like this. But the interesting thing about LOC is it doesn't have to be even real world objects. So sure, it's going to like these items, yes, but it also will like these kind of fictitious items, but it will not like these scrambled items because, again, it cares about there being coherent shape, coherent structure, coherent contours, and not these just jagged, scrambled, nonsense, little pixelated images, okay? Excuse me. Now, when thinking about how LOC is able to do this, how it's able to integrate information from basic lines into coherent wholes, it's important to think about the receptive fields of LOC. Now, just as a reminder, a receptive field is the region of space in which the presence of a stimulus can elicit a response from a neuron. So again, if my hand is the receptive field of a V1 cell, you could say, like, right now, the neuron would not get very excited because there's nothing in it. But if you do something like that, now it would get excited because there is something in it. Now, the biggest difference between receptive fields in V1 and LOC is their size. Basically, while V1 receptive fields are very tiny, LO receptive fields are much bigger, okay? Now, why would that be? Why do LO receptive fields need to get bigger than V1 receptive fields? It's just because by having larger receptive fields, more information can get integrated into a coherent whole in these larger receptive fields. So for example, let's consider a situation where you're looking at a picture of a French bulldog. And here what I've just done is just scattered some small V1 receptive fields on this bulldog on the left and some larger LO receptive fields on the right. And let's just focus on a small number of them. And for example, let's look at this area around here by the mouth. As you can see in LO, this big receptive field is able to combine the responses of all these different oriented lines of the mouth, whereas in V1, each cell is really only seeing one line at a time. And so again, this idea is like, oh, part of the reason that these regions can respond to more complex things than just basic lines is that they have these larger receptive fields that are able to integrate across a larger set of space. And if we return to this image that we were talking about earlier, you can see that the receptive fields here in LGN are smaller than the ones in V1, which are smaller than the ones in LO, and as you can probably guess, are going to be even smaller than the ones in VTC, in the last part of the visual hierarchy. So speaking of, why don't we move now to the last part, the highest level part of the ventral temporal hierarchy, and we'll actually take a break there, and when we come back, we will talk about ventral temporal cortex and object recognition part 2.